So what I'm trying to go after is getting enough of the computational machinery, both in terms of the sets of concepts and their intuitive ground, as well as the actual ability to scribble on paper and calculate across, and then talk about how that relates to modeling physical systems, and then comes what comes across in terms of what's possible once you have made that leap. We've talked about issues of modeling at scale, but there are other things that become possible. For example, there's a lot of work being done in this particular area of computing that I want to focus on in terms of modeling certain kinds of biological processes, both in terms of processes within cells or across larger subsystems like inflammatory processes and multiple sclerosis and things of that nature. So there's a lot of work going on there, but what becomes interesting and possible, especially in the context of what is sort of the mission statement of biology. You have basic questions like what is life, and there are some thinkers who are beginning to propose. I mean, a really good example, another sort of harbinger, sort of outlier kind of thinker is Christopher Alexander, and his proposal is that life is an objectively observable property of configurations of space-time. So he's proposing that there are abstract characteristics, that we can measure with certain kinds of yardsticks to say, when a given configuration of space-time has more life. And that's he's not alone. There are other sort of well recognized, again, sort of established outsiders who are also taking this kind of perspective. David Deutsch, the father of sort of practical quantum computation, also in his Fabric of Reality puts forward this idea that life is an objectively measurable, observable property of configurations of space-time. So, to tie that in, I mean, the point is that at a certain level of abstraction, when we apply these notions of computation to modeling biological processes, it becomes possible to think about axiomatizations of living systems. When do we have a system that we might computationally recognize as alive? And suddenly we have a range of toolkit, a range of tools that make it possible to begin to go after those kinds of questions that are not present, at least in the same way, in the Newtonian toolbox. And also there are a number of other interesting tools. One is the notion of equivalence that lines up with our deeply held scientific intuitions. So in science, we think about the scientific method in terms of what is consensually validatable. So we want to propose theories and then exercise them in terms of observations. A twist on that, just a slightly different perspective is we want to ask. We would like to be able to say, that two systems are somehow the same if we can't find a distinguishing experiment. If any observation we can make of one, we can make of the other, and likewise. Well, this idea is closely related to the notion of bisimulation, which is the natural notion of equivalence of computations that arises in this framework that I want to talk about in subsequent sections. And then also, I think there's a lot. Again, sort of the meta level comment is that I want to couch some of this in terms of intellectual history. Sort of how have our thoughts developed about various kinds of analysis.